In this video, we are going to discuss about the phasor relationship of the inductor, capacitor, and the resistor. Now, let's discuss. Okay, before we really go into the phasor relationship between the RLC circuit, I would like to request you all to study the polar form of the complex number and then the exponential form of the complex number. For the polar form of the complex number, I've given it in the slide number 7, 8, 9, and 10. And then for the exponential form, you can try to read it yourself. Now, okay, let's come back to today's video. In a purely resistive AC circuit, that current and then the applied voltage are in phase. Now, whenever we talk about the phasor relationship, you'll come across the word the lagging and then the leading, and then they are in phase. Now, what is mean by in phase? Now, to calculate that one or to check that one, you can just see this circuit here. We have the voltage source VR is connected with the resistor R here. Now in this case, our load is purely resistive. Now, if we try to find the angle difference between the voltage and then the current, you will see that they will be in same angle. Now it is quite confusing. Okay, let's use this figure here, the current and the voltage waveforms here. If we use this figure, when the magnitude of the voltage is 0, your current magnitude is also at 0 angle. See, the magnitude of the current and the voltage, when they are in 0, both are starting from the 0. And similarly, if you check the peak amplitude of the voltage and the current, now somewhere here, if you consider this one, this is the peak amplitude of the current and this is the peak amplitude of the voltage. Now this peak, both the peak are at 90 degree. Now if you consider this one as a, now let's, in order to analyze the phasor relationship between voltage and the current, we have to take care, we have to consider the 360 degree, one complete cycle. Now from here to here it's 180 and from here to here it is again 180. Now in total we have 360. Now 360 is the complete cycle of the waveform, both for current and the voltage. Now if you compare that the peak, the angle of the peak amplitude for both voltage and current, they are at 90 degree, which means we call that, in the technical term, we call it as a current and voltage are in phase. Or we can also consider at the minimum amplitude at 0 here. At 0, when both the current and voltage amplitude are 0, again they are crossing at 180 degree. Here they are starting at 0 degree, which means in the purely resistive AC circuit, that applied voltage and the current are in phase. Now, if you're representing it in a phasor diagram, this is how it looks like. So, for example, you have magnitude of the voltage is 5 volt. So, if you take the exact scale, you can write it here, the 5 centimeter, the VR, and if the amplitude of the current is let's say 2.5 ampere, then you can write here 2.5 centimeter, and then both are in the same angle, which means at 0 degree. See, they are at 0 degree, current and voltage are in same phase. Now let's see about the inductive load. In a purely inductive AC circuit, the current IL lags the applied voltage VL by 90 degree. Now that is, now if you are writing this degree in the form of radian, is pi by 2. Here you have supply voltage VL here and then current IL here, and then the load, the connected load is purely inductive. Now if you draw the phasor diagram, it says that it is lagging the current IL is lagging the applied voltage by 90 degree. Now we can also refer other term, like here we are using current IL is lagging the applied voltage VL by 90 degree. Or if you're using the term lead, we can say that voltage VL is leading the current by 90 degree. It's okay. It's quite confusing. If you're using the term lag, current IL is lagging the voltage. And if you're using the term lead, VL is leading the current. After all, the meaning is same. Like in case of purely inductive AC load, in case of purely inductive load, your IL is lagging the applied voltage by 90 degree. So how to verify this one? Okay, let's see here. Let's consider now again. Let's consider the 360 degree here, one complete cycle. Now, when the let's consider the peak amplitude. When the VL is at maximum amplitude at 0 degree, your current has a maximum amplitude IL here at somewhere at 90 degree. So in this case, if you compare between the angle between the current and the voltage, this peak amplitude of the VL is crossing the 0 degree before the current IL. It's okay. Or in other words, okay, let's again try to compare between the at the minimum amplitude. Now, when VL is crossing the when the VL, the minimum amplitude of VL is crossing at 90 degree here, whereas for the current it is crossing only after, again there's a phase difference of 90 degree, is crossing at 180 degree, which means if you compare between the phase angle between current and the voltage, if you compare the phase angle between current and the voltage, this voltage is leading or is crossing the 90 degree before the current. So current is crossing only at 180 degree, which means there's a phase difference of 90 degree plus 90 degree. So this is how we use the term lead. So VL is leading the current IL with the phase difference of 90 degree plus 90 degree. Or if you're using the term lag, current IL is lagging the applied voltage VL by minus 90 degree. So I hope I have cleared your confusion. And then now this is the phasor diagram that we have. IL lags VL by 90 degree. So this is IL, and then here we have VL. If you consider here the 360 degree like this, so IL is lagging the VL by plus 90 degree. So VL is already at 90 degree, whereas the current is at 0 degree. So that means there's a phase difference of plus 90 degree. And then if you measure from VL to IL, it will be minus 90 degree. Okay, in a purely inductive circuit, the opposition to the flow of alternating current is called the inductive reactance. Now, this is similar to the resistance that we have. Be it capacitor or the inductor, they are also the type of resistance, right? Now, in a purely inductive circuit, the opposition to the flow of the AC alternating current is called the inductive reactance. And then the magnitude of the XL, that the inductive reactance, is given by 2 pi F times the value of the inductor. And then the unit is in ohms. So here is a small exercise. So you can simply substitute these things, these given parameters in the given formula here, and then try to calculate the XL. Okay, here again numericals that you can try to solve this. And then, okay, let's check about in a purely capacitive AC circuit. Now, in the purely capacitive AC circuit, the current IC leads the applied voltage by 90 degree, or in other words, you can say that your voltage VC is lagging the current IC by 90 degree. So similarly, you can also calculate the magnitude of the XC here. XC is called the capacitive reactance. Now this is the opposition to the flow of alternating current. Um, so you can try to calculate this one using 1 by 2 pi fc. This f is the system frequency. So okay, let's see the waveform for this one. If this is the circuit diagram for the VC connected in series with the capacitor here, capacitive load here, and then if you try to draw the phasor diagram for the purely capacitive load, your IC will be leading the VC by 90 degree. Or from the waveform here, we can say that if you consider the one complete cycle, 360 degree here, when okay, let's consider here when for the minimum amplitude, when the IC is 0, it is at 0 angle. Now if you compare it with the VC, is coming only at 90 degree, which means that the current, the capacitive current is leading the capacitive voltage by 90 degree. There's a phase difference between the phase difference of 90 degree between the inductor, between the applied voltage and the capacitive current. So similarly, you can also try to solve the capacitive reactance here. You simply have to substitute these parameters in the given formula that we have in this formula. Okay, you have more numericals to solve here. Okay, now this is the term how you can remember these things. So we are using the term civil in order to get the relationship between the leading and the lagging between the capacitor, inductor, voltage, current, okay, voltage and the current. Now we are representing it with the term civil. Okay, in a capacitor, you can just remember this term. In a capacitor, this capacitor is represented by the C. The current I is ahead, which means is leading the voltage, and the voltage is leading the current for the inductor. See, is now you should make it perfect to use the term both leading and lagging with reference to voltage and the current. In case of the capacitive load, we have in the slide I have written that current is leading the capacitor, but current is leading the voltage. But if you're using the voltage first, then voltage should be lagging the current. You should use you should know how to use the term both lagging and leading in the same component. So you can just try to read this, and I think it's not difficult to understand. Now in the next video, we will see the series RL circuit. Now, once we have the complete idea about the purely inductive and the purely resistive phasor diagram, it's quite easy for us to understand these RL circuits. So, okay, see you in next session.